All right, so welcome to Math 150, Section 2, Lecture 14, 2021. Today we are going to do the fundamental theorem of calculus. We are mostly going to prove it. We are not going to completely rigorously prove it. I will highlight where I am assuming small little bits. We are also not going to prove it in the greatest generality. Because if I prove it in the greatest generality, you're going to have very weak conditions on functions and then have to use big results from analysis. So instead, I'm going to use conditions that are satisfied in practice. We will then test the fundamental theorem of calculus's predictions in a couple of settings where we can figure out without too much trouble what the actual area is and see that it actually works. Whenever you have something, you want to test it. I will review some of the key theorems from Calc 1 and Calc 2. When we get to multivariable integration, I am not going to develop the theory of multiple integration. I'm going to basically just say we've seen it now when we did one-dimensional, just do it twice or three times and whatnot, rather than lines, use rectangles and boxes. This is always a challenge as to how much detail do you want to get into. I think one really good, strong, solid theoretical lecture is more than enough in a class like this. And if you want to see more theory, I'm happy, of course, to chat, but I think one pass is enough. Has anybody here seen a rigorous proof or close to rigorous proof of the fundamental theorem of calculus? So this equals the number in the first section, which was also 0. So when you have a theorem with the name fundamental, you don't get that for nothing. We don't know that many fundamental theorems. We should have a sense of why they're true. So the first thing we do is the intermediate value theorem. And one of its main consequences, the mean value theorem. Have you seen these before? So anybody remember what the intermediate value theorem is?
If like f is continuous.
Good. So you start off immediately with the conditions. If f is continuous on an interval a, b, then what?
Then there has to be a point f of c, like that's between f of a and f of b.
Okay, so what was it? Then given any c, big C, between f of a and f of b, there is a c in the interval ab such that f of little c equals f of big C. So essentially what it means is there's no jumps. So here's a, here's b, and imagine my function is like this. So down here is f of a, up here is f of b. You give me any value between them, and there has to be at least one choice of c, such that f of little c equals f of big C. I'm not going to prove this, but this sounds very reasonable. If I start below c, and I stay below c, how can I jump up to f of b? All right, the next one is the mean value theorem. So if f is continuous and differentiable on AB, then there is a C in AB such that f of B minus f of A over B minus A is f prime of C. Now, what's annoying about both of these theorems is it doesn't tell you how to find C. It doesn't tell you where C is. It just tells you there is some C that works. And if you want to look at the function, so maybe here is A, here is B. This is going to be the average speed. The slope of that line, f of b minus f of a divided by b minus a, the change in y over the change in x, the change in distance over the change in time, that's my average speed. And the mean value theorem says that at some point in time, you must be traveling at the average speed. Your instantaneous speed must equal the average speed at some point. It doesn't say that there's only one point where that happens. It just says there's at least one point. So I'm going to give a rough proof. So let's assume the average speed is 50 miles per hour. There are two cases. I'm either always traveling at 50 miles per hour, or I'm not always traveling at 50 miles per hour. Imagine you're always traveling at 50 miles per hour. So here's one, always at 50 miles per hour. Can you give me some moment in time where my instantaneous speed equals my average speed if I'm always traveling at 50 miles per hour? All the time, any time works. Any C will work. So case 2, we're not always at 50 miles per hour. But what would it mean if we're not always at 50 miles per hour? Could we always be below 50 miles per hour? If our speed is always less than 50 miles per hour, could our average speed be 50 miles per hour? No. What if our average speed was above? What if our instantaneous speed was always above 50 miles per hour? Could our average be 50? No. So what this means is, at some time, we're less than 50, and at another, we're greater than 50. And listen, now what theorem do we use? So we know at some point we're less than 50. We know at some point we're greater than 50. What else do we use? Yeah, intermediate value theorem. Now let's be really careful. What must be true for a function to use the intermediate value theorem? It's continuous. Did we assume that f prime is continuous? We just assumed f is continuous and differentiable. We didn't assume the derivative was continuous. So, continuously. So let's just put in continuously differentiable. And I'll leave it for you to ponder, would this result still be true if the function is differentiable, but not continuously differentiable? Yes.
Is there, what kind of function would be continuously differentiable, but the derivative of it would be?
Well, imagine you take the function absolute value of x. That function is continuous, but it's not differentiable.
Yeah.
Integrate that function, integrate absolute value of x. That's now your original function, and the derivative of that function is absolute value of x.
Okay.
So I can start off with a function that is not differentiable. So now the next thing is, can I come up with a function that's differentiable but not continuously differentiable? And we've seen some examples with partial derivatives where the partial derivatives might always exist, but depending on how things are defined, partial derivative is not continuous. And we saw that leads to horrible, horrible problems in multivariable calculus. So you can't have a function that's differentiable but not continuously differentiable. So absolute value of x would actually be continuous. So I would need something a little bit different. So I might want to choose maybe like a split function, and then somehow like play games with integrating that. Yeah.
How does it need to be, like, f prime need to be continuous?
Well, because we're using the intermediate value theorem and we're applying that to f prime.
Oh.
Because we're talking about the speed. So we're applying the intermediate value theorem to f prime, so we need f prime to be continuous. Now, you might have heard of Rolle's theorem. It's a special case when f of a equals f of b equals 0. And so, in this case, we would actually have 3 times where the first derivative is 0. So how many of you have seen Rolle's theorem in your calculus class? Okay. So it's a very special case of the mean value theorem. It's just a special case with f of a equals f of b equals 0. One of the reasons I wanted to mention this is, if I give you the general case like this, if I just change my coordinate axes and do the function like this, it's now a Rolle's theorem. So what I want to do is I want to show you how you can get the mean value theorem in general from the special case of Rolle's theorem. And in the interest of time, I'm going to do it a little bit faster than I did in section 1. So I'm going to construct a new function. G of x is f of x minus f of a. And I'm going to fix this because this is not quite right. When you look at this, is g of a equal to 0? Yeah, it's just f of a minus f of a. So here, g of a is 0, but g of b is not necessarily 0. It's f of b minus f of a. So what I want to do is I want to subtract something so that it's going to equal 0 when x equals b. But what I subtract can't contribute at all when x equals a. Well, if I subtract x minus a over b minus a, when x equals a, this is 0, so I'm subtracting nothing. And when x equals b, I'm subtracting 1. Well, if f of b minus f of a equals 1, I'd be done. So in general, I just put f of b minus f of a over here. And so if I look at this function, I'm basically subtracting off a straight line from it. I now have g of a equals g of b equals 0. So by Rolle, there exists a c such that g prime of c equals 0. But when I take the derivative, what's the derivative of f of x? It's just f prime. And so I evaluate that at c. What's the derivative of f of a? Constant, so it's just 0. Now I take the derivative of this piece. F of b minus f of a is a constant. B minus a is a constant. What's the derivative of x minus a? 1. So I get f prime of c minus f of b minus f of a over b minus a. Ah, here's the mean value theorem. So if you know Rolle's theorem, you actually have the mean value theorem. This is a really good principle in mathematics. Often it's enough to do a special case, and then you can reduce whatever you need to study to that special case. One last thing to just mention about the mean value theorem. We can rewrite f of b minus f of a over b minus a equals f prime of c as f of b equals f of a plus f prime at some point c times b minus a. Does this remind you of anything we've seen before? What does this remind you of? Tangent line, excellent. So if you look at the tangent line, it was f of b is approximately equal to f of a plus f prime of a b minus a. So the difference is, with the tangent line, it's approximate, and I'm using all information at the point A. With the mean value theorem, it's exact, but I don't know which point to use. Okay. There's one last concept we're going to use, and it's going to be the concept of what it means for a function to be bounded. So informally, a function is bounded if I can find some number and it never gets larger than that number. So most of the functions we're looking at, as long as the function doesn't blow up, if we're looking at it on a finite interval, they're going to be bounded. If I look at the function e to the x grows exponentially. But if I look at e to the x from 0 to 2, it's going to be at most what? How large could e to the x be from 0 to 2? E squared. So f is bounded by b if for all x in our interval a, b, we have the absolute value of f of x is less than equal to b. And in the proof of the fundamental theorem of calculus, all we're going to need is that certain functions are bounded. The actual bound doesn't matter. Anything that's finite works. In one of my favorite papers that I wrote, I needed to prove something was finite. I proved it was most approximately 10 to the 602. And I could have done better than 10 to the 602, but I just needed a finite number. So I did the most crude estimation possible. 10 to the 602 is finite. Okay. Let me say I give you the function f of x is cosine x cubed e to the x plus x squared minus 1. And I want to see is this function bounded. Well, if I take absolute values, the absolute value of a sum is less than or equal to the sum of the absolute values. I lose the possibility for cancellation. So this would be less than or equal to cosine of x cubed e to the x plus the absolute value of x squared plus 1. What's the largest? And let's say 0 less than or equal to x less than or equal to 2. Let's say x is between 0 and 2. What's the largest cosine x can be? 1. What's the largest e to the x can be? E squared. Do you think cosine x cubed times e to the x, do you think that's ever as large as e squared? No, because cosine of x is largest when x is 0, e to the x is largest when x is 2. But if I replace each one of these by their largest value, then that product is clearly going to be larger than the best x I can take here. So this would be less than or equal to 1 cubed times e squared. What's the largest x squared can be? 4 plus 1. Again, this is terrible because I've got x squared minus 1. X squared minus 1, if x is 0, this is negative 1. If x is 4, is 2, it goes all the way up to 3. I'm replacing it by 5. Its largest value is 3. This is bad estimation, but if I only need a finite number, this is finite. And that's more than enough. Okay. So what we're going to do now is I will state the fundamental theorem of calculus, and then I will go through and describe how to prove it. And when we're stuck, what do you think we will use? Mean value theorem, right? I am not trying to surprise you or trick you, right? When you are stuck, go with the mean value theorem, right? So, fundamental theorem of calculus. Assume f is continuously differentiable. Assume f prime is bounded. Assume big F prime equals little f. Let integral from a to b f of x dx be the area under y equals f of x from a to b. Then this equals big F of b minus big F of a. So the area under the curve is y equals f of x. So the area under the curve from a to b is big F of b minus big F of a. Is there a unique function whose derivative is little f? So do we have unique antiderivatives? How do antiderivatives differ if they have the same derivative? You differ by constant. So I could add 17 to f to big F, and that won't change its derivative. If you look over here, it's big F of B minus big F of A. If I add 17 to big F, then I add 17 to F of B, and I add 17 to F of A, so when I subtract, they cancel. If you've done physics, this should remind you of potential energy. It doesn't matter where you set the zero level to be for potential energy. When we do physics problems, what matters is the change in potential energy. And so I only care about the differences. It's the same thing here. So what I'm going to do is we will do the special case A equals 0, B equals 1. If I can handle that special case, I can do the more general case. And what we're going to do is we're going to chop up the interval. Here's 0, here's 1, 1 over n, 2 over n, k over n, k plus 1 over n. And we're going to chop up our function like this. And we're going to study what goes on each of these subintervals. And we're going to let n go to infinity. So let's zoom in. So here is k over n, here's k plus 1 over n. And let's say my function looks like this. Okay. So what I want to do is I want to find the area under the curve in this interval. Well, what we'll do is we will find an upper bound and a lower bound for this area. And we'll show that as n gets larger and larger and larger, the upper and the lower bounds converge to a common value. If the upper bound is always at least as large as the area, and the lower bound is never more than the area that lives between the two of them, right? I'll use my face mask, okay? So my face mask is the true area, it lives between the upper and the lower. If the upper and the lower converge, what's the only thing they can converge to? You know, if the upper and the lower converge to the same value, what must that same value be? The true area is at least as large as the lower bound. The true area is no more than the upper bound. So if you have the area here and you have the lower bound as a function of n and the upper bound as a function of n, and if the upper and the lower bound converge to a common value, what is the only possibility for that common value? The area. The area is sandwiched in between. It's got to go to that as well. So if we can show that the upper and the lower bounds converge to a common value, that common value is the area. All right. So how do we do that? So this is where I'm going to assume a result. I'm going to assume that on any interval, I always have a point where my function is lowest and a point where it's greatest. That's something you prove in analysis. But as long as I have a closed interval, there will be a point where my function is smallest, there will be a point where my function is largest. If we have an unbounded set, that's not necessarily the case. But because my interval is bounded, there will be a largest and smallest. So if I use this for my height, this rectangle would be a lower bound for the area. And if I use this for my height, that rectangle would be an upper bound for the area. So f at Lk times the width, which is 1 over n, is less than the area of the kth piece, which is less than f of uk times its width, which is 1 over n. So do we agree that the area is going to live between these two? And now if we sum, we're going to use some notation. So the summation k goes from 0 to m of ak means a0 plus a1 all the way up to plus am. So we've seen that notation when we've done least squares. This is a nice, concise way of writing the sum, rather than writing the dots. So for example, if I wrote the sum k goes from 0 to 2 of ak, that means take the index and just replace it first with 0, then with 1, then with 2, and this would just be a0 plus a1 plus a2. Okay? It's just good, concise notation. So now I want to sum this over all values of k. So the sum k goes from 0 to n minus 1 of f of lk times 1 over n is thus equal to the area, is thus equal to the sum k goes from 0 to n minus 1 of f of uk times 1 over n. And now what we want to do is we want to prove that these two converge to the same value. And if we can show that they converge to the same value, that gives us a way to calculate the area. So as we take more and more points, it's going to be more and more accurate. Now, there are some technical things you do have to be a little bit careful about. It would be nice if the lower bound was always moving towards the true area, and the upper bound was always falling down towards the true area. It's not necessarily the case. The lower bound could actually dip down for a little bit. The upper bound could actually grow for a little bit. You can avoid this by, rather than taking, first split up into 5 points and 6 points and 7 points and 8 points, if you just do powers of 2, 2 points, 4 points, 8 points, 16, and so on, you won't have this problem. It's a technical issue, doesn't really matter. Just I want to make sure you do not claim more than is true. I'm not claiming that the lower bound moves straight towards the area. It could actually backtrack for a little bit before it converges. I'm just saying it converges in the limit. So we want to show that the upper and the lower sums converge to the same value. So a lemma is a small result that's used on the way to prove a good result. So lemma un minus ln goes to 0 as n goes to infinity. Which is, can the lower sum ever be larger than the upper sum? No. So we know 0 is thus equal to the upper sum minus the lower sum. All right, well, let's look. The upper sum is the sum over k. The lower sum is the sum over k. All right, so they're both a sum over k. So 0 is equal to the sum. K goes from 0 to n minus 1 of f uk 1 over n minus f of lk 1 over n. Okay. Notice both of these factors have a 1 over n. If I have a sum, if I multiply every term in the sum by 5, what happens to the value of the whole sum?
Increases by a factor 5.
Decreases by a factor 5. What if I divide every term in the sum by 5? Then it decreases by a factor 5. So because every term has a 1 over n, I can just pull out that 1 over n, and I get 0 is equal to 1 over n. The sum k goes from 0 to n minus 1 of f uk minus f of lk. Hi, yes.
Why was the 1 over n in there in the first place?
So what is the width of each of these intervals? I'm going from k over n to k plus 1 over n. So each box has a width 1 over n. So each box is 1 over n. Any other questions up to this point? Any thoughts about how we might analyze f of uk minus f of lk? How should we analyze it? What should we use? Well, I'm not trying to trick you. When in doubt, what's the guess? Mean value theorem. I have f of uk minus f of lk. So by the mean value theorem, there is a ck between lk and uk such that f of uk minus f of lk over uk minus lk equals f prime of ck. we write that as f of uk minus f of lk in absolute value is equal to f prime of ck absolute value times uk minus lk. So now, let's think. Here's k over n, here's k plus 1 over n. lk is somewhere, some point in here. uk is some point in here. How far apart can lk and uk be? What's the furthest apart uk and lk could be? So where would you put lk and uk in this interval to make them as far apart as possible? Yeah, kn and k plus 1 over n. So the maximum distance here is this is at most 1 over n. Right? The largest separation we can have between uk and lk is 1 over n. What about here? We're assuming that this is at most big B by assumption. We're assuming the first derivative is bounded. So when we put this all together, we get 0 less than equal to 1 over n, the sum, k goes from 0 to n minus 1 of big B times 1 over n. I technically don't have an absolute value here, but because this is at least as large as this is clearly non-negative. I can regard that as an absolute value if I wish. What can we do now? This is b times 1 over n. Does this have any k dependence? We're just adding b over n every single time. So this is the same as b over n squared times the sum, k goes from 0 to n minus 1 of 1. What's the sum from 0 to n minus 1 of 1? Not n minus 1. It's just 1, because we're going up to n minus 1. So you would think it's n minus 1, but we're starting at 0. So my son learned many years ago when he was young that if I told him you can do it 3 more times, he would start counting at 0. But Daddy, it's 0, 1, 2, 3. So you always want to be careful as to how we're doing this. We're going up to n minus 1, but we're starting at 0. So we get that this is just b divided by n squared times n. So the sum was actually large in some sense. You might have thought, well, it's going to be really small because we have this 1 over n, but we have n terms, and that cancels that 1 over n, but we had that extra 1 over n from the width. And so when the dust settles, bn over n squared, well, this is just b divided by n, and this goes to 0 as n goes to infinity. And what's nice is it doesn't matter what b is. As long as b is a finite number, this is going to go to 0. Okay, so what we've just shown is that the upper and the lower sums converge to a common value, and that common value has to be the area. Any questions on what we've done so far? So now we need to show that you can compute the area by using the antiderivative. So I will try to keep things on the board as long as possible. So what do you think we should use now? Mean value theorem. So far we've applied the mean value theorem to little f. What could we apply the mean value theorem to now? Big F. So let's apply mean value theorem to big F. So big F of k plus 1 over n minus big F of k over n is equal to little f at some special point, I'll call it ck star, times what's the distance between k plus 1 over n and k over n? How far apart are those points? One over n. So it's k plus 1 over n minus k over n, which is just 1 over n. So I've applied the mean value theorem to big F. Why is this useful? Well, let's look and see what happens if we do this sum. So we would have f of 1 over n minus f of 0 over n, plus big F of 2 over n minus big F of 1 over n, plus big F of 3 over n minus big F of 2 over n, plus big F of 1 minus big F of n minus 1 over n. What do you notice in this sum? Yeah, this diagonal cancellation. We have a plus f1 over n, a minus f1 over n. These terms cancel. This is called a telescoping sum. A plus f of 2 over n, a minus f2 over n. These cancel, and you're left with just big F of 1, and right there is just big F of 0. So if I sum this over n, it's just going to be big F of 1 minus big F of 0. So the mean value theorem is being extremely valuable for us. So we've just shown big F of 1 minus big F of 0 is the sum, it goes from 0 to n minus 1, of f of ck star times 1 over n. But we know f of lk has to be less than equal to f of ck star has to be less than equal to f of uk. Because on the interval, this is where the function is smallest. This is where the function is largest. So this has to be in between. If I sum this, if I multiply everything by 1 over n, and I sum, when I sum, this just becomes the lower sum. This just becomes the upper sum, and this just becomes f of 1 minus f of 0. So f of 1 minus f of 0 is sandwiched between the lower sum and the upper sum. What do the lower and the upper sum converge to? They converge to the area. Well, if this lives between the lower and the upper sum, and the lower and the upper sums converge to the area, what's the only thing that f of 1 minus f of 0 can be? And here's the fundamental theorem of calculus. And we still have over 10 minutes left in class, and we proved the mean value theorem and talked about the intermediate value theorem before. The big gap was saying that there's always a point where the function is smallest and always a point where the function is largest. If you look at the nice functions we study, that's true. But to prove things in general, that's something you have to demonstrate. All right. So again, my goal is to concentrate the really advanced theory into just one lecture, take our hit one time, and then we'll move back to actually applying this and solving integration problems. Now that we've had the fundamental theorem of calculus, though, it would be nice to know, can we trust it? Does the result seem reasonable? Is it surprising how easy it is now to find some areas? Well, let's test the fundamental theorem of calculus. So can somebody give me the easiest function you think I will let you as a way to test the fundamental theorem of calculus? F of x equals 1. If you said f of x equals 0, I would say that's not a fair test. That's too easy. And if you tried f of x equals what this would be the next one. Instead of 1, you could have tried 2. Well, no, I mean, more advanced than just 1. X. That should not be your first test. That should be your second. So if we try f of x equals 1, big F of x, what function has derivative 1? X. So the integral from 0 to 1 of f of x dx would just be big X, would be just x at 0 and 1 is just 1. Let's check. Let's plot this. So here's 0, here's 1. Here's my function, which is identically 1. And so we have now successfully calculated the area of the unit square using the fundamental theorem of calculus. Thank you. Okay. Should anybody be thrilled and convinced that the fundamental theorem of calculus was worthy of this long digression if we're using it to just calculate the area of a square? No. This is not enough to convince you that this is worth doing. So now let's look at the next function. F of x equals x. Big F of x is 1/2 x squared. Now, when we do it, we get the integral from 0 to 1 of f of x dx. This is going to be 1/2 x squared at 0 and 1 is 1/2. Anybody know what kind of shape we're about to get? Triangle. Who sings a song about triangle? Music group. Okay, 0, 1, 1. What is the area of a triangle with base 1 and height 1/2? So we can use the fundamental theorem of calculus to calculate areas of triangles. All right, is this worthy of celebration yet?
I think so.
If this is all we can do, is you should know how to do these shapes with significantly less work. We need something more interesting. Any thoughts about what we should try next?
I think that's equals x squared.
Yes, let's try f of x equals x squared. And this will be our first real test. And we'll get 1/3 x cubed. And now, if we use the fundamental theorem of calculus, we get the integral from 0 to 1 of f of x dx is 1/3 x cubed at 0 and 1 is 1/3. And so if I plot what we've done, here's 0, here's 1. We've now found the area under a parabola. Do you know the formula for the area under a parabola?
You can just do the rectangle.
But I'm saying, if I give you a parabola, you know an explicit formula for the area. For a rectangle, you know the formula. For a triangle, you know a formula. Do you know a formula for the area under a parabola? Yes, by the fundamental theorem of calculus. But if we want to test the fundamental theorem of calculus, we need a way to independently calculate the area under a parabola. So you had made a good suggestion. What should we try?
You could just take the rectangle, like from 0 to 1, and then like subtract the function.
What do you mean by take the rectangle from 0 to 1?
Like from 0 to 1 and then 1 up.
If we take the rectangle from 0 to 1, is that rectangle going to be down here like this? And then 1 up here. But then we just know it's between 1 and 0.
And then you'd subtract. Right?
Are you saying just draw a big rectangle here?
Yeah.
So it's not just one big rectangle and one small rectangle?
Well, no, and then you subtract the function, like, right?
Not quite. I might be misunderstanding what you're saying. What could we do? What have we learned to find areas? How are we computing areas? We can do the Riemann sum. So we can do, this might have been what you're trying to say, we can just sum all these rectangle areas. You can sum the rectangle areas. And these are called Riemann sums. So if we're able to calculate these sums, then we can use that to test the fundamental theorem of calculus. So we would need to take the limit as n goes to infinity, the sum k goes from 0 to n minus 1 of f of lk times 1 over n. Now when you look at the parabola on each interval, where is the parabola largest? At the beginning of the interval or at the end of the interval? At the end. Where's the parabola smallest, at the beginning or the end? Beginning. So this would be the same as the limit as n goes to infinity, the sum k goes from 0 to n minus 1. So it would just be, Lk would just be the left endpoint. It would just be k over n, and we square it, because our function is f of input is input squared. Does everyone see how I got this? This f of Lk is just k over n, and f of x is just x squared. The function is smallest at the left input. So when you look at this, k is going to change as we vary over k, but the n's down below don't change. How many n's do we have? 3. So this is the same as the limit as n goes to infinity, 1 over n cubed, the sum, k goes from 0 to n minus 1 of k squared. So now we need to just figure out what is the sum of k squared. So there's a couple of key formulas. And so 1 plus 2 plus plus m is m plus 1 over 2. So the sum of the first powers up to m is m plus 1 over 2. Can I start the sum at 0? Yeah, it's not going to change it. I could do 0 squared plus 1 squared plus m squared, and that turns out to be m plus 1, 2m plus 1 over 6. And this is usually proved by something called induction. We might cover that later in the semester. We can at least test and see if this is reasonable. If m equals 0, what should the left-hand side be? So if m is 0, it's just 0 squared, which is, and if we put m equals 0, we get the right-hand side is 0. If I take m equals 1, what do we get? 1. And we get 1 times 2 times 3 over 6, because that's 1. We'll do one more. If I take m equals 2, I would have 0 squared plus 1 squared plus 2 squared. What's that? 5. I would have 2 times 3 times 5. Well, 2 times 3 cancels with the 6, and we get 5. So this is not a proof, but it at least works for the first couple. So this is equal to the limit as n goes to infinity. So m is just going to be n minus 1. So we would have n minus 1 times n, 2n minus 1 plus 1, 2n minus 2 plus 1, so it's 2n minus 1. And we would divide by 6n cubed. We have n cubed from here, and we have the 6 from there. So now we just want to figure out what is this equal. Well, this is the same as the limit as n goes to infinity. Let's multiply things out in the numerator. N minus 1 times 2n will be a 2n squared times n will be a 2n cubed. We'll have a minus 2n and a minus n, so it's a minus 3n times n, a minus 3n squared. And then minus 1 times minus 1 is plus 1 times n is plus n over 6n cubed. Well, it's really nice. There's only one term in the denominator. So I can write this as the limit as n goes to infinity. Let's do it term by term. 2n cubed divided by 6n cubed is 1/3. 3n squared divided by 6n cubed would just be 1 over 2n. And the last is n over 6n cubed is plus 1 over 6n squared. Well, if n goes to infinity, what does 1 over 2n go to? It goes to 0. And what does 1 over 6n squared go to? And so when the dust settles, you get 1/3. So this is the first legitimate test of the fundamental theorem of calculus. If we're only able to test it for rectangles and triangles, I'm not that excited. I know how to calculate areas of rectangles and triangles. This just gave us the area under the parabola. And before knowing calculus, that's an extremely hard problem. What other figure do you think we might want to apply this to? What other figure do you want to know the area of?
Anything?
Or what's a really good, important figure? I'm sorry? I can't hear you. Trig function. In particular, which trig function is the big one we want to study? What geometric object, considered by many the perfect object? Circles. Can we find the area of a circle? You have to be very careful, I apologize for the pun, not to have a circular argument. That when you are doing anything in your proof using calculus for the area of a circle, that you don't assume functions, you don't assume facts about these trig functions that you could only prove by knowing things such as the area of a circle. So you've got to be very careful when you're doing this. All right, this is a good place to stop.